Hello and welcome. In this video, we'll be exploring the world of quadratics. By the end of this session, you will be able to, first, solve quadratic equations using various methods like factorization, completing the square, and the quadratic formula. Second, use the discriminant to determine the nature of a quadratic's roots and its graph's relationship with the x-axis. Third, find the sum and product of the roots of a quadratic equation without solving it. Fourth, sketch quadratic functions by identifying key features like the vertex and intercepts. Fifth, find the equation of a quadratic function from its graph or given information. Sixth, solve problems involving the intersection of quadratic and linear functions. And finally, apply quadratic optimization to solve real-world problems. These are the core concepts we'll cover, and they are fundamental to your IBAA-HL mathematics studies. Let's begin with the most basic concept, the quadratic equation. A quadratic equation is any equation that can be written in the standard form ax squared plus bx plus c equals 0, where a, b, and c are constants, and a is not equal to 0. The solutions to this equation are called the roots, or zeros. These are the values of x that make the equation true. For example, let's consider the equation x squared minus 3x plus 2 equals 0. If we test the value x equals 2, we substitute it into the equation. We get 2 squared minus 3 times 2 plus 2, which simplifies to 4 minus 6 plus 2, which equals 0. Since the equation holds true, x equals 2 is a root. So a root is simply a value that satisfies the equation. Our goal is to find all such values. There are several methods to solve quadratic equations. We'll start with factorization, which you may have seen before. The key principle here is the null factor law. It states that if the product of two factors, a and b, is 0, then at least one of the factors must be 0. This law is incredibly useful because it allows us to turn a quadratic equation into two simpler linear equations. Let's look at an example. Solve 3x squared plus 5x equals 0. First, we factorize the left side by taking out the common factor, x. This gives us x times the quantity 3, x plus 5 equals 0. Now, we apply the null factor law. Either the first factor, x, is 0, or the second factor, 3x plus 5, is 0. So we have two possibilities, x equals 0, or 3x plus 5 equals 0. The first solution is already found. For the second, we solve the linear equation. Subtracting 5 from both sides gives 3x equals negative 5, and dividing by 3 gives x equals negative 5 over 3. Therefore, the two roots of the equation are x equals 0 and x equals negative 5 over 3. Let's try another factorization example, this time with a trinomial. Solve the equation x squared equals 5x plus 6. The first step in factorization is always to rearrange the equation so that one side is 0. This is crucial for applying the null factor law. Subtracting 5x and 6 from both sides gives us x squared minus 5x minus 6 equals 0. Now we need to factorize this trinomial. We are looking for two numbers that multiply to negative 6 and add to negative 5. Those numbers are negative 6 and positive 1. So the factorized form is the quantity x minus 6 times the quantity x plus 1 equals 0. Applying the null factor law, we set each factor to 0. This gives us x minus 6 equals 0, or x plus 1 equals 0. Solving these linear equations, we find our two roots, x equals 6 and x equals negative 1. Here's a very important caution when solving quadratic equations. Consider the equation x squared equals 5x. A common mistake is to divide both sides by x. If we do this, we get x equals 5. This is a solution, but it's not the only one. The problem is that we divided by a variable, x. If x were 0, we would be dividing by 0, which is undefined. By dividing by x, we implicitly assumed x is not 0, and in doing so, we lost the solution x equals 0. The correct method is to rearrange the equation to 0 and factorize. Subtracting 5x from both sides gives x squared minus 5x equals 0. Factoring out x gives x times the quantity x minus 5 equals 0. Applying the null factor law, we find the two correct solutions, x equals 0 and x equals 5. Always rearrange to 0 before factorizing to avoid losing roots. Sometimes, a quadratic equation might not look like a quadratic at first glance. Let's see an example. Solve for x. 3x plus 2 over x equals negative 7. To eliminate the fraction, we can multiply every term in the equation by x. This is a valid operation, as long as we remember that x cannot be 0. Multiplying by x gives us 3x squared plus 2 equals negative 7x. Now we have a standard quadratic equation. Let's rearrange it to the standard form. Adding 7x to both sides gives 3x squared plus 7x plus 2 equals 0. We can solve this by factorization. We need two numbers that multiply to 3 times 2, which is 6, and add to 7. Those numbers are 1 and 6. We can rewrite the middle term, 7x, as x plus 6x. Then we factor by grouping. This gives us the factored form. The quantity x plus 2 times the quantity 3x plus 1 equals 0. Applying the null factor law, we find the solutions are x equals negative 2 and x equals negative 1/3. Neither of these is 0, so they are both valid solutions. Not all quadratics can be easily factorized. For those cases, we have other methods. One powerful technique is called completing the square. The goal of completing the square is to convert a quadratic equation into the form x plus p squared equals q. This form is easy to solve by taking the square root of both sides. Let's start with a simple example where the square is already complete. Solve the equation the quantity x plus 2 squared equals 7. To isolate x, we first take the square root of both sides. Remember, when you take a square root, you must consider both the positive and negative solutions. So x plus 2 equals plus or minus the square root of 7. Finally, we subtract 2 from both sides. This gives us the exact solutions. X equals negative 2 plus or minus the square root of 7. This method gives us exact answers, which is often preferred in higher-level mathematics. Now let's apply the completing the square method to a quadratic in standard form. Solve for exact values of x squared plus 4x plus 1 equals 0. Step 1. Move the constant term to the right-hand side. Subtracting 1 from both sides gives x squared plus 4x equals negative 1. Step 2. Complete the square on the left-hand side. To do this, we add the square of half the coefficient of x to both sides. The coefficient of x is 4. Half of 4 is 2, and 2 squared is 4. So we add 4 to both sides. This gives us x squared plus 4, x plus 4 equals negative 1 plus 4. Step 3. Factorize the left-hand side, which is now a perfect square trinomial, and simplify the right-hand side. The left side factors to the quantity x plus 2 squared, and the right side simplifies to 3, so we have x plus 2 squared equals 3. Step 4. Solve for x by taking the square root of both sides. X plus 2 equals plus or minus the square root of 3. Subtracting 2 gives our final exact solutions. X equals negative 2 plus or minus the square root of 3. What if the coefficient of x squared is not 1? The process is very similar. Let's solve the equation negative 3x squared plus 12x plus 5 equals 0. Step 1. Divide the entire equation by the coefficient of x squared, which is negative 3. This makes the coefficient of x squared equal to 1. Dividing by negative 3 gives x squared minus 4x minus 5/3 equals 0. Step 2. Move the constant term to the right-hand side. Adding 5/3 to both sides gives x squared minus 4x equals 5/3. Step 3. Complete the square. Half of the x coefficient, negative 4, is negative 2. Squaring it gives 4. So we add 4 to both sides. We get x squared minus 4x plus 4 equals 5/3 plus 4. Step 4. Factorize the left side and simplify the right side. The left side is x minus 2 squared. The right side is 5/3 plus 12/3, which is 17/3. So x minus 2 squared equals 17/3. Step 5. Take the square root of both sides. X minus 2 equals plus or minus the square root of 17 over 3. Step 6. Isolate x. We can also rationalize the denominator. Adding 2 to both sides gives x equals 2 plus or minus the square root of 17 over 3. Rationalizing gives x equals 2 plus or minus the square root of 51 over 3. While completing the square is a powerful method, it can be tedious. Fortunately, we can use it to derive a general formula that works for any quadratic equation. This is the quadratic formula. For any equation in the form ax squared plus bx plus c equals 0, the solutions are given by x equals negative b, plus or minus the square root of b squared minus 4ac, all divided by 2a. Let's prove this formula by completing the square on the general equation. Starting with ax squared plus bx plus c equals 0. First, divide by a, x squared, plus b over a, x plus c over a equals 0. Move the constant term x squared plus b over a, x equals negative c over a. Complete the square. Half of b over a is b over 2a. Squaring it gives b squared over 4a squared. Add this to both sides. Factor the left side and find a common denominator on the right. This gives x plus b over 2a squared equals b squared minus 4ac all over 4a squared. Take the square root of both sides. The square root of the denominator is 2a. Finally, subtract b over 2a from both sides to get the quadratic formula. This formula is a powerful tool that will always give you the solutions. Let's use the quadratic formula to solve an equation. Solve for xx squared minus 2x minus 6 equals 0. First, identify the coefficients a, b, and c. Here, a is 1, b is negative 2, and c is negative 6. Now substitute these values into the quadratic formula. X equals negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times negative 6 all over 2 times 1. Let's simplify the expression under the square root, which is called the discriminant. Negative 2 squared is 4. Negative 4 times 1 times negative 6 is positive 24. So we have 4 plus 24, which is 28. We can simplify the square root of 28. 28 is 4 times 7, so the square root of 28 is 2 times the square root of 7. This gives us x equals 2 plus or minus 2 times the square root of 7, all over 2. Finally, we can divide the numerator by 2. This gives our exact solutions. X equals 1 plus or minus the square root of 7. The quadratic formula is incredibly useful, but the part under the square root sign b squared minus 4ac is especially important. It's called the discriminant. We use the Greek letter delta, a triangle, to represent the discriminant. So delta equals b squared minus 4ac. The value of the discriminant tells us about the nature of the roots without having to solve the entire equation. There are 3 cases. Case 1. If the discriminant is positive, delta is greater than 0. This means we are taking the square root of a positive number, which gives 2 distinct real values. So the equation has 2 distinct real roots. Case 2. If the discriminant is 0, delta equals 0. The square root of 0 is 0, so the plus or minus part of the formula disappears. We are left with only one solution, x equals negative b over 2a. This is called a repeated or double root. Case 3. If the discriminant is negative, delta is less than 0. We are trying to take the square root of a negative number. In the real number system, this is impossible. Therefore, the equation has no real roots. The discriminant is a powerful tool for quickly understanding the nature of a quadratic solutions. Let's use the discriminant to determine the nature of the roots for a couple of examples. First, consider the equation 2x squared minus 2x plus 3 equals 0. Here, a equals 2, b equals negative 2, and c equals 3. Let's calculate the discriminant. Delta equals b squared minus 4ac, which is negative 2 squared minus 4 times 2 times 3. This simplifies to 4 minus 24, which is negative 20. Since the discriminant is negative, delta is less than 0. This tells us there are no real roots for this equation. Now for the second example. Consider the equation 3x squared minus 4x minus 2 equals 0. In this case, a equals 3, b equals negative 4, and c equals negative 2. Let's find the discriminant. Delta equals b squared minus 4ac, which is negative 4 squared minus 4 times 3 times negative 2. This simplifies to 16 plus 24, which is 40. The discriminant is positive. Delta is greater than 0. This means there are two distinct real roots. Since 40 is not a perfect square, these roots will be irrational. The discriminant is especially useful when a quadratic equation contains an unknown constant. We can use it to find the values of that constant that result in a specific type of root. Let's consider the equation x squared minus 2x plus m equals 0. We want to find the values of m for which the equation has a repeated root, two distinct real roots, and no real roots. First, let's find the discriminant in terms of m. Here, a equals 1, b equals negative 2, and c equals m. Delta equals b squared minus 4ac, which is negative 2 squared minus 4 times 1 times m. This simplifies to 4 minus 4 meters. Now we can answer the questions. A. For a repeated root, the discriminant must be 0. So 4 minus 4 meters equals 0. Solving for m, we find that m must be 1. B. For two distinct real roots, the discriminant must be positive. So 4 minus 4 meters is greater than 0. Solving this inequality, we find that m must be less than 1. C. For no real roots, the discriminant must be negative. So 4 minus 4 meters is less than 0. Solving this inequality, we find that m must be greater than 1. Let's tackle a more complex example involving an unknown constant. Consider the equation kx squared plus the quantity k plus 3 times x equals 1. We need to find the values of k for which the equation has two distinct real roots, two real roots, a repeated root, and no real roots. First, rearrange the equation into standard form. Subtracting 1 from both sides gives kx squared plus the quantity k plus 3 times x minus 1 equals 0. Now, find the discriminant in terms of k. Here, a equals k, b equals k plus 3, and c equals negative 1. Delta equals b squared minus 4ac, which is the quantity k plus 3 squared minus 4 times k times negative 1. Expanding this gives k squared plus 6k plus 9 plus 4k, which simplifies to k squared plus 10k plus 9. To solve the inequalities, it's helpful to factorize the discriminant and draw a sign diagram. The discriminant factors to the quantity k plus 9 times the quantity k plus 1. The sign diagram shows that the discriminant is positive when k is less than negative 9, or k is greater than negative 1, and negative when k is between negative 9 and negative 1. Now we can answer the questions. A. For two distinct real roots, delta must be positive. So k is less than negative 9, or k is greater than negative 1. B. For two real roots, delta must be greater than or equal to 0. So k is less than or equal to negative 9, or k is greater than or equal to negative 1. C. For a repeated root, delta must be 0. So k equals negative 9, or k equals negative 1. D. For no real roots, delta must be negative. So k is between negative 9 and negative 1. There's a fascinating relationship between the roots of a quadratic equation and its coefficients. If we let the roots of ax squared plus bx plus c equals 0 be alpha and beta, then the sum of the roots, alpha plus beta, is equal to negative b over a. And the product of the roots, alpha times beta, is equal to c over a. Let's prove this. If alpha and beta are the roots, we can write the quadratic in factored form. A x squared plus b x plus c equals a times the quantity x minus alpha times the quantity x minus beta. Now, let's expand the right-hand side. This expands to a times the quantity x squared minus the sum of the roots times x plus the product of the roots. Dividing both sides by a, we get x squared plus b over a, x plus c over a equals x squared minus the sum of the roots times x plus the product of the roots. By equating the coefficients of x and the constant terms on both sides, we get our formulas. The coefficient of x on the left is b over a, and on the right is negative alpha plus beta. So alpha plus beta equals negative b over a. The constant term on the left is c over a, and on the right is alpha beta. So alpha beta equals c over a. Let's see how to use these formulas with an example. Find the sum and product of the roots of 25x squared minus 20x plus 1 equals 0. First, identify the coefficients. Here, a equals 25, b equals negative 20, and c equals 1. a equals 25, b equals minus 20, c equals 1. Now let's find the sum of the roots. The sum alpha plus beta is negative b over a. This is negative 20 over 25, which simplifies to 20 over 25, or 4/5. Next, let's find the product of the roots. The product, alpha beta, is c over a. This is 1 over 25. We can check this by actually solving the quadratic equation using the formula. The roots are 2 plus or minus the square root of 3, all over 5. Adding them gives 4/5, and multiplying them gives 1 over 25. The formulas work perfectly. Now let's shift our focus from equations to functions. The graph of a quadratic function is called a parabola. A quadratic function is written as y equals a x squared plus bx plus c. Let's define some key features of a parabola. The point where the graph turns is called the vertex. If the parabola opens upwards, the vertex is a minimum point. If it opens downwards, it's a maximum point. The vertical line that passes through the vertex is the axis of symmetry. A parabola is perfectly symmetrical about this line. The point where the graph crosses the y-axis is the y-intercept. This occurs when x equals 0, so its coordinates are always 0, c. The points where the graph crosses the x-axis are the x-intercepts. These are the roots of the equation ax squared plus b x plus c equals 0. The coefficient a in the function y equals ax squared plus bx plus c tells us a lot about the parabola's shape. If a is positive, the parabola opens upwards. We call this concave up. If a is negative, the parabola opens downwards, which is concave down. The absolute value of a controls the width of the parabola. If the absolute value of a is between 0 and 1, the parabola is wider than the basic parabola y equals x squared. If the absolute value of a is greater than 1, the parabola is narrower. There are three main forms for writing a quadratic function, each highlighting different features. The general form, y equals ax squared plus bx plus c, gives us the y-intercept, c, and the axis of symmetry, x equals negative b over 2a. The factored form, y equals a times the quantity x minus p times the quantity x minus q, directly gives us the x-intercepts, p and q. The vertex form, y equals a times the quantity x minus h squared plus k, directly gives us the vertex, hk, and the axis of symmetry, x equals h. Let's practice sketching a parabola using its intercepts. Sketch the graph of y equals 2 times the quantity x plus 3 times the quantity x minus 1. This function is in factored form, which makes finding the x-intercepts very easy. The x-intercepts occur when y equals 0. Setting y to 0, we get 2 times the quantity x plus 3 times the quantity x minus 1 equals 0. Using the null factor law, the x-intercepts are at x equals negative 3 and x equals 1. Next, let's find the y-intercept. This occurs when x equals 0. Substituting x equals 0, we get y equals 2 times 3 times negative 1, which is negative 6. So the y-intercept is at 0 minus 6. We also know that the coefficient a is 2, which is positive, so the parabola opens upwards. Now we can sketch the graph. We plot the x-intercepts at negative 3 and 1, and the y-intercept at negative 6. Then we draw a smooth, upward opening parabola through these points. The axis of symmetry is midway between the x-intercepts, at x equals negative 1. Now let's sketch a parabola using its vertex form. Sketch the graph of y equals negative 2 times the quantity x plus 1 squared plus 4. This function is in vertex form, y equals a times the quantity x minus h squared plus k. This form directly gives us the vertex. Comparing the forms, we see that h is -1 and k is 4, so the vertex is at the point -1, 4. The axis of symmetry is the vertical line passing through the vertex. So the axis of symmetry is the line x equals -1. Next, let's find the y-intercept by setting x equals 0, y equals -2 times 1 squared plus 4, which is -2 plus 4, or 2. The y-intercept is at 0, 2. Finally, the coefficient a is -2, which is negative, so the parabola opens downwards. We plot the vertex at -1, 4, and the y-intercept at 0, 2. Since the parabola is symmetrical about x equals -1, there must be another point at -2, 2. We then draw a smooth, downward opening parabola through these points. What if the quadratic is in general form, y equals ax squared plus bx plus c, and we need to find the vertex? We can use a formula. The x-coordinate of the vertex is given by the formula x equals -b over 2a. Let's find the vertex of the function y equals 2x squared minus 8x plus 1. Here, a equals 2 and b equals -8. The x-coordinate of the vertex is -8 over 2 times 2, which is 8 over 4, or 2. To find the y-coordinate, we substitute this x value back into the original function. Y equals 2 times 2 squared minus 8 times 2 plus 1. This is 8 minus 16 plus 1, which equals -7. So the vertex is at the point 2 minus 7. Let's do a full sketch from general form. Consider the quadratic y equals 2x squared plus 6x minus 3. First, the axis of symmetry. X equals -6 over 2 times 2, which is -3 halves. Axis of symmetry. X equals -3 halves. Next, the vertex. Substitute x equals -3 halves into the function. Y equals 2 times -3 halves squared plus 6 times -3 halves minus 3. This simplifies to 9 halves minus 9 minus 3, which is -15 halves. The vertex is at -3 halves minus 15 halves. The y-intercept is easy. When x equals 0, y equals -3. Y-intercept, 0 minus 3. For the x-intercepts, we set y equals 0. This gives the equation 2x squared plus 6x minus 3 equals 0. Since it doesn't factorize easily, we use the quadratic formula. The solutions are x equals -3 plus or minus the square root of 15 all over 2. These are approximately -3.44 and 0.44. Now we can sketch the graph. We plot the vertex, the intercepts, and draw a smooth upward opening parabola, as a is positive. Another way to find the vertex from the general form is to convert the function to vertex form by completing the square. This also shows us the transformations from the basic parabola y equals x squared. Let's write y equals x squared plus 4x plus 3 in vertex form and sketch it. We complete the square on the x terms. Half of 4 is 2, and 2 squared is 4. We add and subtract 4. This gives y equals x squared plus 4, x plus 4 plus 3 minus 4. The part in the parentheses is a perfect square, x plus 2 squared. The constants combine to -1, so the vertex form is y equals the quantity x plus 2 squared minus 1. From this form, we can see the vertex is at -2, -1. The y-intercept is still 3. The graph of y equals x squared plus 4, x plus 3, is the graph of y equals x squared shifted 2 units to the left and 1 unit down. The vertex moves from 0, 0 to -2, -1. What if the coefficient of x squared is not 1? We factor it out first. Convert y equals 3x squared minus 4x plus 1 to vertex form. First, factor out the 3 from the x terms. This gives y equals 3 times the quantity x squared minus 4/3 x plus 1. Now complete the square inside the brackets. Half of negative 4/3 is negative 2/3. Squaring it gives 4/9. We add and subtract 4/9 inside the brackets. This gives y equals 3 times the quantity x squared minus 4/3 x plus 4/9 minus 4/9 plus 1. The perfect square is x minus 2/3 squared. We multiply the negative 4/9 by the 3 outside the brackets, which gives negative 4/3. Then we add the 1. This simplifies to y equals 3 times the quantity x minus 2/3 squared minus 1/3. From this vertex form, we can see the vertex is at 2/3 minus 1/3. We've seen that the discriminant tells us the number of real roots. Graphically, this corresponds to the number of times the parabola intersects the x-axis. If the discriminant is negative, delta is less than 0. There are no real roots. The graph does not cut the x-axis. If the discriminant is 0, delta equals 0, there is one repeated real root. The graph touches the x-axis at exactly 1 point. If the discriminant is positive, delta is greater than 0, there are 2 distinct real roots. The graph cuts the x-axis twice. This connection between the algebra of the discriminant and the geometry of the graph is a key concept. This leads us to the concepts of positive definite and negative definite quadratics. A quadratic is positive definite if its value is positive for all real values of x. This means the entire parabola lies above the x-axis. For this to happen, 2 conditions must be met. First, the parabola must open upwards, so a must be positive. Second, it must not touch or cross the x-axis, so the discriminant must be negative. A quadratic is positive definite if and only if a is greater than 0 and delta is less than 0. Similarly, a quadratic is negative definite if its value is negative for all real values of x. This means the entire parabola lies below the x-axis. For this, the conditions are: first, the parabola must open downward, so a must be negative. Second, it must not touch or cross the x-axis, so the discriminant must be negative. A quadratic is negative definite if and only if a is less than 0 and delta is less than 0. Let's use the discriminant to determine the relationship between a graph and the x-axis. Consider the function y equals x squared plus 3x plus 4. First, let's check the coefficient, a. Here, a equals 1, which is positive. This means the parabola opens upwards. A equals 1 greater than 0, so the graph is concave up. Next, let's calculate the discriminant. Here, b equals 3, and c equals 4. Delta equals b squared minus 4ac, which is 3 squared minus 4 times 1 times 4. This is 9 minus 16, which is negative 7. Since the discriminant is negative, delta is less than 0. This means the graph does not cut the x-axis. So we have an upward opening parabola that never touches the x-axis. This means the entire graph is above the x-axis. Therefore, the quadratic is positive definite. Its value is always positive. Now, let's work in reverse. Given a graph or some information about it, can we find the equation of the quadratic function? The key is to choose the right form of the quadratic equation based on the information you have. If you are given the x-intercepts, use the factored form. If you are given the vertex, use the vertex form. If you are given 3 general points, use the general form. In all cases, you'll need to find the value of a by substituting the coordinates of another point on the graph into your equation. Let's start with an example where we are given the x-intercepts. Find the equation of the quadratic function whose graph has x-intercepts at -1 and 3 and a y-intercept at 3. Since we have the x-intercepts, we'll use the factored form. The x-intercepts are p equals -1 and q equals 3. So the equation is y equals a times the quantity x plus 1 times the quantity x minus 3. Now we need to find a. We use the other piece of information, the y-intercept is 3. This means the point, 0, 3, is on the graph. Substitute x equals 0 and y equals 3 into our equation. We get 3 equals a times 1 times -3. This simplifies to 3 equals -3a, so a equals -1. Now we have the full equation. The quadratic function is y equals negative 1 times the quantity x plus 1 times the quantity x minus 3. We can expand this to the general form, y equals negative x squared plus 2x plus 3. Let's try an example where we are given the vertex. Find the equation of the quadratic function whose graph has a vertex at 3, minus 2, and passes through the point 0, 16. Since we have the vertex, we'll use the vertex form. The vertex is h, k equals 3 minus 2. So the equation is y equals a times the quantity x minus 3 squared minus 2. Now we need to find a. We use the other piece of information. The graph passes through the point 0, 16. Substitute x equals 0 and y equals 16 into our equation. We get 16 equals a times negative 3 squared minus 2. This simplifies to 16 equals 9a minus 2. Adding 2 to both sides gives 18 equals 9a, so a equals 2. Now we have the full equation. The quadratic function is y equals 2 times the quantity x minus 3 squared minus 2. We can expand this to the general form. Y equals 2x squared minus 12x plus 16. Let's consider a problem where we need to find the intersection points of a quadratic function and a linear function. Find the coordinates of the points of intersection of the graphs with equations y equals x squared minus x minus 18 and y equals x minus 3. At the points of intersection, the y values of both functions must be equal. So we can set the two equations equal to each other. This gives us x squared minus x minus 18 equals x minus 3. Now we have a quadratic equation. Let's rearrange it to standard form. Subtracting x and adding 3 to both sides gives x squared minus 2x minus 15 equals 0. We can solve this by factorization. We need two numbers that multiply to negative 15 and add to negative 2. Those numbers are negative 5 and positive 3. The factored form is the quantity x minus 5 times the quantity x plus 3 equals 0. This gives us x equals 5 or x equals negative 3. These are the x coordinates of the intersection points. To find the full coordinates, we substitute these x values back into one of the original equations. The linear equation is simpler. When x is 5, y is 5 minus 3, which is 2. So one point is 5, 2. When x is negative 3, y is negative 3 minus 3, which is negative 6. So the other point is minus 3 minus 6.